Here's an interesting problem, guys. I've just recorded this whole video for you, 39 minutes long with no sound. So I am now going to annotate and talk over again and hope that I can turn around and do what I need to do for you. So here is a lesson relating to all the stuff we've done before. You must know what a sine curve looks like, you must know what a cosine curve looks like, and you must do everything in your power to learn the triangles, to know how to transform, dilate, and what a function looks like. Okay? Imagine we have the function y equals root 2 sine of x plus 1, right? And we've been asked to sketch this. Well, we know that it has a base function of sine x, and we know what this root 2 means. Hopefully we're aware that there is an amplitude change, and the plus 1 will mean a vertical translation of 1 unit. Now, when I draw these, I try and look at, well, breaking the problem down, and I always start off by thinking, well, what does a sine curve look like? Well, a sine curve has a period of 2 pi. It crosses at 0, pi, and 2 pi. And as we can see from there, it has a maximum and a minimum of -1. It would also have a range of -1 to 1. So, well, the root 2 suggests that we are going to change that. So I now, literally, what I'm doing here is showing you what I would do. I would now change that to root 2 and minus root 2. And that would look at this translation of 1 unit. Well, okay, let's draw another set of axes, and yes, Finlay, here we go. Here is the dotted line to show that you are aware that the graph has been shifted up by 1 unit. Alright, we know that on the standard it would cross on pi and 2 pi. That doesn't actually change because I'm not changing the period of my graph. We know that because between the sine and the x there is no number, or in fact the number is 1. So having now got my axes, as it were, sorted out, I'm going to try and really badly draw a sine curve. Right? You're going to be able to do this much better than I am. Sadly, my graphics tablet and me do not necessarily always get on. So having moved the whole thing up, whereas the maximum was at root 2 before, it now becomes root 2 plus 1. And in the same way, what was negative root 2 will become negative root 2 plus 1, which, as I'm about to show you now, wow, the value of hindsight, can be written as 1 minus root 2. And I've only put it in brackets there, just to give you an idea that it's a side thing. All right, right, okay, perfect. So there's my sine curve. We know that it's going to cross there, so my advice to you is write 0, 1, and that's actually wrong, entertainingly. No, it's not. That's 0, 1. Awesome. But we now notice the graph cuts into different points, as I've circled there in purple. So how do I find those? Well, we know that they cross the x-intercepts. So that's going to be important to me at the moment, but maybe I should also make sure that when I'm drawing my graphs, better safe than sorry, to make sure that I put on where my maximum and minimums are. And in this situation, we know that my maximum will happen at pi on 2, and my minimum will happen at 3 pi on 2. So let's go back to solving for the intercepts. We know that the x-axis has the equation y equals 0, which means that we are just going to equate the whole function to 0. Using a little bit of algebra and a rather nifty pen color change, if I do say myself, I can move the plus 1 to the other side and it becomes minus 1. And I can also move my root 2 over and it becomes minus 1 over root 2. Right, what does that mean? Well, let's find a solution. I've got 1 and root 2, so let's draw my first triangle, the 60, 30 one. Nope, that's no good to me because I don't have a root 2 in there, so it must be my other triangle, the one that has a 1, and a root 2 and 45 degrees. Well, if we remember that sine is opposite over hypotenuse, the opposite is 1, the hypotenuse is root 2, and that must give me a solution of, absolutely, pi on 4. Well, there's my first solution, it's pi on 4, but, well, what domain have I been given? Well, in this situation, let's say the domain is going to be between 0 and 2 pi. And so we add that in, and we're saying, right, okay, well, we've got pi on 4 as my first solution. Let's draw my all stations to Canberra graph, or unit circle as it turns out. And we find that, well, if sine is going to be negative, it's got to be in the tan and cosine quadrants. So I know that that value there is going to be my pi on 4, and likewise on the other side, that's going to be pi on 4. So, well, I now need it to fit and give me the right values. Well, if I go around my circle, I find out that yes, from there, around it's pi plus that little bit of pi on 4, which gives me 5 pi on 4, for those of you who are unaware. And again, to find the other side, I would be looking at the value of 2 pi minus pi on 4, and that gives me, well, I tend to like to rewrite this in terms of on 4s, and I know that 2 pi is 8 pi on 4, and that just means that I do 8 pi minus the pi to give me 7 pi. So my two solutions now are pi on 4 and 7 pi on 4. Do I need any more? Well, in this situation, no. We know that there are two solutions between 0 and 2 pi, which means that I can now say, well, I have my solutions as 5 pi on 4 and 7 pi on 4. And so I finished my question. Yay, I can move on. No, I can't, because if you remember on the pop quiz, some of you forgot that a coordinate has both an x and a y value, and even though my graph is incredibly small, I would suggest making sure that you write on them the actual crossing points, the values of the crossing points, and in this situation it would be, 5 pi on 4 over 0 and 7 pi on 4 comma 0, right? So without knowing what that graph roughly looks like, with regards to the translation of 1 and the root 2, you're going to find it really, really quite complicated to then go on and sketch an appropriate graph. What would happen if I had the graph of y equals 2 sine 2 open brackets x minus root 4 close brackets minus root 3? It looks pretty complicated, but once again, if you know what each of those components mean, you should be able to have a rough idea of how to sketch it. So we know it's a sine curve. We know that the amplitude is going to be doubled, all right, because it's a dilation of 2 away from the x-axis. We know that there's going to be a translation of pi on 4 to the right, or in the positive x direction. We know that that 2 between the sign and the bracket is a dilation of factor 2. Now that does not double, remember, it does not double the sine curve's period. It actually halves it, and that minus root 3 will move it down root 3. Now if you remember that the 2 sine curve graph is going to be fitting between 0 and 2 pi, that is my domain, and we learned last lesson that the period would be given by 2 pi over the root of n, right? And so in this situation, because n is 2, and I meant modulus of n, and because I know n is 2, then we get 2 pi over 2, and as such we get pi. So how would we solve this? It's going to be too time consuming to try and draw this graph at this moment in time, so let's just look at how we would solve this. Well, we know that this will have to be put equal to 0 if we're looking for our x-intercepts, and having done that, I move the minus root 3 over to become a positive root 3, and the 2 outside the sine function to move outside the to move to the other side. Now, as you can see, I've moved the 2 over to become root 3 upon 2, and let's try and find a solution. There we go. There's my triangle, 1, 2, root 3, and 60 degrees. And so we know that for root 3, it'll have to be the opposite over the hypotenuse, because that's my sine function. For root 3 to be the opposite, it would have to be 60 degrees, leaving x as being pi on 3. So my first solution is pi on 3. Yep, that seems to fit as well with my unit circle. So I have my first solution as pi on 3. What is my second solution? Well, a quick diagram. All stations to Canberra. And what do we notice? Yep, well in this situation sine is positive, so it'd have to be in the A and S quadrants. I've already got pi on 3, but in this situation I would have to do pi minus pi on 3, or as I've decided to put 3 pi on 3 minus pi on 3, which gives me 2 pi on 3. So those are my two solutions. Are there more? Yes, there are more, because remember, our period has changed. There would be another two solutions, but for brevity of this, I really don't want to solve the whole problem. I just wanted to give you an idea. But what we would do to each of the values pi on 3 and 2 pi on 3 is we would add 2 pi to get the next two values. Once having those four values, I would divide by 2, I would add the pi on 4, and that would give me my four values of x. Again, this was a quick gallop through But ideally, you need to know your algebra skills. If you don't know how to, divide by 2 and add the pi on 4 and use your unit circle, this really is testing absolutely everything that we've done so far. And these are the type of questions that will be in a SAC, and probably the more challenging ones in a final examination, right? We've now got to a point where you can do exercise 6H, and I suggest doing questions 1A and D, and questions 2A, D, and G. These are not exhaustive, right? These are the ones I suggest you do to get a flavour, but over the holiday I would suggest doing many, many, many more questions. Some time ago we talked about the idea of addition of ordinates, and we dealt with examples with x squareds and x's and whatever else, and I want to take it all the way back to basics. If I had something really, really simple like the line y equals x plus 2, we know that that is effectively the lines y equals x and the lines y equals 2 added together. So as you can see here, what I'm doing is I've drawn my line y equals x, which is the green line, and the line y equals 2, which is the blue line. Okay? And what I need to do is think, well, when you add ordinates, you're effectively taking the y values of y equals x and the y values of y equals 2 all the way along that graph, and you are adding them together. Right? Now in many cases I always start here where it says 0, 0, because I know what the value is there for y equals x. It's 0. At that point there, the y value is 0. And I know for the line y equals 2, the y value is 2. So when x equals 0, which is effectively the y-axis, I know that when I do 0 plus 2, I get 2. Hence I can now plot my first cross. If I look at that point there, right, I know that the point is intersecting. I know that in this situation, when x equals 2, y equals 2, and that's true of both graphs. So again, I have 2 plus 2, so I can automatically put a value of 4. Now you don't actually need to know the values. You can effectively guess just by saying, well, I know that for each value on that line y equals x, I'm going to add 2 onto it, and the similar on the other side. Even with the negatives, I've got a positive value of blue and a negative value of green. In this situation, they're going to cancel out to be 0, right? And once I've drawn 4 points, then you can see that gold line there now stands for the graph y equals x plus 2. Now I know some of you last time found this quite challenging, but you're actually just adding y values together. That's all. So now when we have something more complicated, like for example y equals 2 sine x plus 3 cos 2x, and you're asked to draw, 2 separate graphs and then using addition of ordinates find their sum. Well, if we say the period is between 0 and 2 pi, you're going to find this complicated unless, again, you know roughly speaking what the graphs of y equals 2 sine x are and the graphs 3 cos 2x are. So there we go. Let's look at my 2 sine x. Well, we know that it's a standard sine x curve. There's no dilation to or away from the y-axis, and so I have my standard crossing points at 0, pi and 2 pi, and in this situation, because my amplitude has been doubled, right, or it's been dilated away from the x-axis, I know 2 and minus 2. So there we go. I now know what my first graph looks like. What about the graph of 3 cos 2x? Well, we know that the standard graph of cos x looks very much like I'm drawing now, 0 and 2 pi, because that's the standard period, and we know that it crosses at pi on 2, 3 pi on 2, and pi. It has an amplitude of 1 normally and minus 1, but in this situation we're going to have our graph as a maximum minimum at 3. That 2, all right, remember now, changes the period of my graph, and using the formula that the period is 2 pi over n, and I know that n is 2, my period would become pi. So all of my values effectively half, or more importantly, between my domain of 0 and 2 pi, I will fit 2 of those graphs in. Just because I'm doing a quick sketch, I now means I can go through my own graph and just half all of my values to see where they're going to cross. Now, I'm limited with my resources here to be able to do what I can in the graph. All right, I'm not going to be able to try and draw these particularly effectively, and so I'm just making sure I know where the key points are on my graph, and I'm making sure I realize that cosine curve there are going to be two of. Okay, now using the power of technology, here's one I created earlier, and let's make it a bit bigger. Now the problem is that as soon as I make it bigger, it doesn't look necessarily as clear, but this was taken from the Essentials textbook. What can I see? Well, let's just remind ourselves of the equation that I was given. Y equals 2 sine x plus 3 cos 2x. And when we look on our graph, they've even color-coded it for us to try and give us a visual representation. So, a good choice of using yellow, that's what I've chosen. So the yellow graph stands for the y equals sine 2x, and yep, there it goes. It's a standard graph. It's got an amplitude of 2. It crosses in all the places we're expecting it to place, and so, yep, that looks pretty good for me. The cosine 2x curve is in red, all right? And as again we're expecting, if we follow the curve, we find that in this situation it has a period of pi. All right, and there are two of them fitting in the space of the 2 pi. Maximum of 3 and minimum of -3, and so that all seems to fit really, really nicely. Now when we add these two together, we're actually effectively looking at the blue line. So let's just check. When we have the yellow graph, we know at pi on 2, we have a maximum of 2, and for the 3 cos 2x, we have a value there of -3. And we're just adding those together. When you're adding ordinates, you're adding the y values. So when I add 2 and -3, what do I get? -1. And so it's no coincidence that I can now put a blue cross at -1, which is exactly where that blue line is. Well, again, I'm looking for places where graphs cross 0, because that makes my life a lot easier, because I just know that in this situation, the blue dot will be where the yellow graph and the red graph add together. Well, my yellow graph is at 0, has a y value of 0 at pi, and my red graph has a value of 3 at pi. So 0 plus 3 is 0, and that's why it's there. Now, when you look more closely at this, what do you tend to notice with the blue line? Well, it's certainly cyclical, it's certainly periodic, but it seems to go low, and then high, and then very low, and then up. How would we be able to predict this? Well, you can't. You just have to look and say, well, hold on a moment. For 3 pi on 2, there are two negative values. I have -2 for 2 sine x, and I have -3 for 3 cos 2x. And when I add -2 and -3, because again this is addition of ordinates, what do I get? -5. And yep, so that's why the blue graph there is at -5. Right? This isn't necessarily rocket science. It seems confusing, but it's just adding y values together. All right? Would you get one of these questions in your VCE? Who knows? You would hope not, because they're pretty time consuming. But as a practice, I suggest you're now able to do exercise 6I, question 1, 3, and 5, and be very careful with 5, because 5 is taking the ordinates away, not adding. So you could argue, why is this called addition of ordinates? 6I is a short exercise, but you like to use the time over the holiday to have a go at those questions you don't quite follow or you've struggled with. Alright, okay, so what about if they give you a graph and you have to find the equation from it? Well, again, the miracle of technology means I have an example that I can extract from the Essentials textbook, and here we go. What do I notice? Well, it's cyclical, it's a sine curve, but we have to be very careful there, because sometimes they try and trick you. Remember, a cosine curve is just a sine curve translated by pi on 2, and I suppose you could argue the same way vice versa. So sometimes sine curves can be described as a cosine function, but in this situation we probably won't. But one important point to note is if you look at that x-axis, what do you notice? It's not in terms of pi, and it doesn't have to be in terms of pi. This is going back to the idea that maths can trick you. Right, well, I'm going to tell you that that graph has a function of t in terms of a sine nt. Well, there's my function of t, and there's my y value. Yep, we can see that it doesn't seem to have a translation vertical. It seems to be centered around 0, or centered around y equals 0, and it seems to have some sort of, amplitude of 6. But let's go back to this period business. We have the period of 10, and we know that the formula for period is 2 pi on the modulus of n. Well, if our If our x-axis is in terms of just a number, it must mean that n is in terms of pi, because they will then cancel each other out. And let's just watch that working. So I now know that my period is 10, I've got my 2 pi, but I don't know what n is. I can get rid of the modulus sign at this moment in time because my answer is probably going to work out to be positive. And as such, when I do 2 pi divided by 10, lo and behold, there we go, my n is pi on 5. Right? That's why my period is a whole number value, and please don't get tricked by that if it comes up in an exam. So I now know I can rewrite this function as a times the sine of pi on 5 times t, and looking at a, we talked about it a little bit a moment ago, my amplitude is going to be 6. So looking at 6, I can rewrite my equation now as my function of time is equal to 6 times the sine of pi on 5 times t. Well, I would do if I hadn't spent so much longer earlier talking about the amplitude. Right? So there we go. Now, hold on a moment. I seem to have written that a little bit strangely. I've got 6 times sine of pi t all over 5, and yet up there I wrote pi on 5 times t. Remember, you can change that pi on 5 times t is exactly the same as pi t upon 5, right? And in the same way as if we take another example and I have pi t on 6, that can be rewritten exactly as pi on 6 times t. Don't be tricked. Okay, so that was a pretty trivial example. Let's look at something a little bit more complicated, and again, by the joys of technology. Okay, so that was a pretty basic example. Let's do another one, and whoa, by the joys of technology, once again, here we have another graph. We're looking at this, again, it seems to be a sine function. This seems to have a translation vertically, and yes, once again, we notice that t is in terms of whole number values. So I'm going to tell you that this must have an equation of the form y equals a sine nt plus the value of b. Well, I think, in many cases this is easier now. I can look at this and go, well, the b value must be 4 because the whole graph seems to have shifted up by 4. What can I look at now? Well, the value of a, if we can look at the value of the amplitude, we know that it's going between 4 and 6, or we know the whole value has a range between 6 and 2, and so if we take those away as 4 and halve them, I get my amplitude as 2. And what about my period? Well, we know again that period is 2 pi upon the modulus of n. We know that the period, by looking at the graph, seems to be 6, so we can now write 6 is equal to 2 pi over n, or in this situation n is 2 pi over 6, and n becomes pi on 3. And so, again, trivial example, but we can now complete this and say my function is the sine 2 sine pi t upon 3 plus 4. Job done. And the good news is you are now able to do some questions to practice this yourself. So our suggestion is exercise at 6J, questions all. Right, now there's a lot in there, but again, it's a suggestion that you get used to the idea of being able to look at graphs and fit equations to them, particularly the tricky ones. You cannot imagine the frustration I currently feel sitting here trying to work out why I didn't have my microphone on when I recorded this for the first time. But looking at this, 25 minutes and only another 14 more to speak again. Right, we know what the sine curve looks like, and we know what our cosine curve looks like. And for those of you who haven't got it already, I've already drawn the sine curve, all right? And here we go with the cosine curve, right? Again, it's very useful for reference. These have to be learnt, they have to be understood, they have to be, almost tattooed in places you use very often. But what about the tan curve? What about tan of theta? Now, I'm pretty sure you guys did this last year in methods 1 and 2, but here is a very quick recap. We know that tan theta is sine theta divided by cos theta. That is a very important formula and one you should make sure you remember. But how does that help me with anything? Does it allow me to infer from any of my working out? Does it allow me to work out what the sine... Does it allow me, knowing the sine and cosine curve, to work out what the tan graph is? Absolutely not. This is one you have to learn. Now, what you don't know is I've just edited out a load of really bad drawing, but that's the power of technology. And here we go. You could argue that this is no better in terms of drawing, But that is roughly what my tan graph looks like, all right? It has asymptotes at pi on 2 and minus pi on 2, and it crosses there at 0, okay? And now you're about to watch me draw just shockingly. Really, look, I'm now about to try and delete it, and oh yeah, here we go. Yep, I'm using Photoshop, and awesomely, I now decide to leave that little box just sitting there. Oh no, I've hidden it, quick, quick. And so here we have another asymptote. Now, bearing in mind a tan graph repeats every 180 degrees, right? So it has a period of pi. What I've actually written on the right-hand side there is the crossing point of pi. Please don't confuse that and think it is the crossing point of, the equation of the asymptote. It isn't, okay? But the important part of all of this is that it has a period of pi. Right? Now the range of a tan graph is all real values. There is nothing that can't come out in terms of a y value. But obviously, as you notice here, it has a lot of asymptotes. All right? Now the first one we know is pi on 2, the second one is minus pi on 2, and there is a general formula for asymptotes. And this is very important if you need to write something in function notation. Because remember, in this situation, the tan graphs have all real values except values that fall on the asymptotes. And the equation for the asymptotes is given by theta equals 2k plus 1 multiplied by pi on 2, where k is a real number. So if we take k as 0, then 2 times 0 plus 1 is pi on 2, and lo and behold, that's my first asymptote. And if I put in k of 1 in there, I get 3 pi on 2. So if we just change this now to 3 pi on 2 to now stand for the asymptote, hence you can see that that will give me the values where x will be my asymptote. And it's based on this pi on 2. Right? Remember, my standard equation of an asymptote is pi on 2. When we later on look at dilating these tan graphs, that pi on 2 will change, but it's relatively simple to work out how it changes. All right? So that's a formula you need to remember. Okay, so looking at the idea of y equals 3 tan 2x, all right, and having to sketch that graph, this is me just giving you an example once again of, you know, what the 2 does. Obviously the 3 we know is going to change the stretch. It's a stretch away from the x-axis, which is quite hard to show in tan graphs, all right? It's not going to be possible for me to keep drawing these things because my graphics tablet does not make drawing graphs particularly easy. But what we remember is that in this situation, the period of a tan graph is now pi over the modulus of n, and a quick change of pen color, because that pink or purple really is not easy to read, gives the period of that graph is going to be pi on 2. Now, using the idea of what we had earlier as our equations of our asymptotes were going to be 2k plus 1 times pi on 2, in this situation here, if you remember, we are going to be effectively dilating it a factor of 2 towards the y-axis. So we're squidging in the graphs by a factor of 2. So whereas an original asymptote would be pi on 2, that would change to pi on 4, and likewise where it was 3 pi on 2, it becomes 3 pi on 4, as I'm showing there. So now our equation changes, if you look on the left hand side, such that x is now equal to 2k plus 1 multiplied by pi on 4. Okay, and if we were to try and draw this between 0 and 2 pi, and I do really badly this, guys, so it just becomes harder and harder to try and draw these. I suggest looking in the methods textbook to try and give an idea. As you can see, second attempt, and I really do not seem to be having a lot of luck. Okay, not bad. So there we go. There are my asymptote lines, which are shown dotted. All right, and I'm going to put pi on 4 there, and as such there must be one on the other side that must be minus pi on 4, and you would then continue a graph offwards to fit into the range of 0 and 2 pi. And as you can see, once again, using Photoshop, I've decided to leave half of the history showing on my screen. God. All right, likewise, if we have y equals minus tan of 3x, if you remember in this situation, the minus is a reflection, so the whole graph would be reflected in the x-axis, and the 3x would change my period of my graph to pi on 3. Or more importantly, what would happen is my asymptote would change from pi on 2 to pi on 6, all right? So because it is effectively scaled in by a factor of 3, it would change my asymptote, and as such my equation then would change to x equals 2k plus 1 multiplied by pi on 6, all right? So be very, very careful with tan graphs that you make sure you know the equation of the asymptotes. Okay, final couple of sections, and I know this video has been long, but we have a lot of work still to cover, and I'm suggesting maybe I can do a couple of these over the holiday just to continue teaching you even though we're not in school. How progressive is that as education? All right, so maths, remember, is a big fat trick, and they are going to try and do things to try and confuse you. And one of the best ways of doing that is to come up with equations with sines and cosines in them, right? Because a lot of people tend to forget the easiest rule of all, and probably the one that was hammered through to you by me quite a lot recently. Now, sine and cosine in one equation. Well, where have I seen sine and cosine before? Well, actually, I know that the tan of theta is equal to the sine of theta divided by the cosine of theta. Nothing is any different if I have 2's. So I can say equally the tan of 2 theta is the sine of 2 theta, there's the 2, divided by the cos of 2 theta. Well, how do I now then get sine and cos and turn it into tan? Well, one of the easiest tricks is basically divide both sides by cos of 2x in this case. So if I have sine of 2x over cos of 2x is equal to the cos of 2x divided by the cos of 2x, so all I've done there is divide both sides by 2x. Well, we know that cos of 2x divided by cos of 2x is 1, and the sine of 2x divided by the cos of 2x is tan of 2x. And there we go, the tan of 2x is equal to 1. Well, using my triangles where I have 1, 1 and root 2, I know that my first solution would be 45 degrees, or in this case pi on 4, and yes, let's just define my range, my domain between 0 and 2 pi. And so I can now say that 2x has a solution of pi on 4, and because I know that my tan graph repeats every pi, I'm just going to add on 4 pi to each of these values, right? And again, we have to go back and think. Between a standard graph of 0 and 2 pi, there will be 2 solutions, right? But because my graph is being dilated, all right, and effectively squidged by a half, it means that I'm changing from 2 solutions and doubling that, and actually will give me 4 solutions. So having got my first solution, I then need to go off and try and find the next 2 solutions. So there's me just saying, well, okay, I need 4 solutions. It's a visual reminder to myself to make sure that I understand. Okay, so I need to add on pi. I'm going to try and remember this as 4 pi on 4, so I'm adding 4 pi to each value. Okay, there we go, 4 pi on 4. So not got a lot of space here at the moment. Let's change it up down here a bit. And so there's my first solution, pi on 4, and then I'll have 5 pi on 4, add on, that's it, 9 pi on 4 and 13 pi on 4, which gives me loads of values. There's my 4 values, but they stand for 2x, remember? So I now have to divide each of those values by 2 to get me into the right values. Right, now actually what this does is move all of my values back into 0 and 2 pi, and there we go. So there are my solutions. What have I actually found? I've just found all the solutions where sine x equals cos 2x. Pi on 8, 5 pi on 8, 9 pi on 8, and 13 pi on 8. Right, now again, there's nothing more that you can do really. This is about practice. Just look anywhere that you see a sine and a cos in an equation. Make sure you know what the domain is. Make sure you know what the dilations are, and just try and turn them into a tan if you can. All right? So again, this is more an algebra trick. Good news for you, more questions, yay! Exercise 6K is now totally possible, where I'm suggesting you'll probably do every question. Oh no, I didn't, I lied, even questions. Once again, even questions, this is not meant for you just to say, well, okay, that's going to get me through. If you have the time, do more, because the more of these type of questions to do, the more you will be prepared later on, all right? So, big smiley face, I drew that for a reason. Okay, now remember, 50% of your SAC is done for this topic. right? You can't afford to throw it away. I know you want to go out. I know you want to do a lot of stuff over the holidays. I know you've got other subjects, but you know, university is going to be where you get to have the fun, not necessarily in year 12. And I'm sorry about that, but there is good news. Mr. Dawning, I've remembered why the smiley face is there, and I've got to talk really quickly. Mr. Dawning has done loads of work on your behalf, and as such, I have put on my scroll page a course builder, which has loads of revision materials for you. So, my advice to you is to log on to Course Builder and look at all the revision that he has for you. I've done now. I'll talk more when I see you next lesson. I know this has been a long video, but I thank you for watching. I look forward to seeing you soon. Any questions, come and see me. Otherwise, have a great day.